So a few months ago, Silver uploaded to YouTube these leaked MIT Integration Bee 2025 problems. Now these obviously aren't the real problems that they're going to use next year. This was just the April Fool's joke, but this is actually a very good mock exam to prepare for next year's MIT Integration Bee. So in this video we're going to be going through the first half of the finals problems. Some of these are actually pretty crazy, so I do recommend that you go check these problems out. I'll link it in the description. Try some of these questions out and then come back when you're done. And yeah, let's get going. First up, the integral between 0 and 1 arcsine 16x to the 5 minus 20x cubed plus 5x dx. Now the first step we're going to do is going to be quite unorthodox, but bear with me. So we're going to say x equals sine theta, so dx equals cos theta d theta. So we end up getting our new bounds as between 0 and pi over 2. We have cos theta from our substitution, and now inside of arcsine we have 16 sine to the 5 theta minus 20 sine cubed theta plus 5 sine theta. Now, if we write this a bit differently using just some trig manipulation, like sine squared theta equals 1 minus cos squared theta, we can write it in this form of 5 cos to the 4 theta times sine theta minus 10 cos squared theta sine cubed theta plus sine to the 5 theta. And what you might notice is this is actually just, if we binomially expand cos theta plus I sine theta to the power of 5, take the imaginary component of it, we get 5 cos to the 4 theta sine theta minus 10 cos squared theta sine cubed theta plus sine to the 5 theta. So this is actually just the imaginary component of this, and we can use the Moivre's theorem to write this as cos 5 theta plus I sine 5 theta. So this here is actually just sine 5 theta. So we end up actually just getting the integral between 0 and pi over 2 cos theta times arcsine sine 5 theta d theta. Now here we have to be a bit careful. We can't just jump and say that arcsine sine 5 theta equals 5 theta, because that's not actually true everywhere. If we go into Desmos real quick, I can show you that if we look at just arcsine of sine x between minus pi over 2 and pi over 2, sure, it is x, but that's not true everywhere. As you can see, between pi over 2 and 3 pi over 2, it's actually pi minus x. So if we go back onto here, we write arcsine of sine 5 theta. We want it between 0 and pi over 2, but we're going to have to split it up into 3 regions. We have 5 theta between 0 and pi over 10, 5 times pi over 5 minus theta between pi over 10 and 3 pi over 10, and 5 theta minus 2 pi between 3 pi over 10 and 5 pi over 10, which is pi over 2. So I have it written up into this white integral here, this red integral here, and this green integral here with their respective bounds. And we can just evaluate all of these fairly easily. It's just basic integration by parts that I'm sure you guys all know how to do. So we have the white result, the red result, and the green result. And what we notice is actually all of these sine terms here, like this sine pi over 10 term will cancel with this one, and this sine 3 pi over 10 term will cancel with this one. So we end up just getting pi over 2 minus 5 minus 10 cos 3 pi over 10 plus 10 cos pi over 10, which is about 0.20351. So yeah, that's the answer for the first question. It's quite strange, but I think it's manageable. Definitely not going to be the hardest one here, that's for sure. So yeah, let's go into the next. Alright, next up, we have the integral between minus pi over 2 and pi over 2 of x times the natural log of 1 plus cos x to the power of sine x. So, this one, I'm going to start off with another substitution. This one's going to be u equals minus x. So du equals minus dx. So what's going to happen to the bounds? So this is going to become pi over 2. This is going to become minus pi over 2. But we can use the minus sign from the substitution to then flip these bounds back to normal. So our bounds are just going to stay the same as before. And then instead of x, we have minus u. Instead of x here, we have minus u. Instead of x here, we have minus u. And we can use the fact that cos is an even function and sine is an odd function to write it as cos x to the power of minus sine x. And we have the minus out front from here. Okay, so since these are the same bounds of integration as before, we can add this red integral here to this green integral to get 2i. So if we do so, we still have x at the front, and then we can use the fact that since this log has a minus at the front, and we're adding it with this one, then we can divide what's inside of both of them. So we have 1 plus cos x to the power of sine x over 1 plus cos x to the power of minus sine x. And we can rearrange this a little bit as well, actually. If we times the top and bottom by cos x to the power of sine x, we end up with cos x to the power of sine x, and then we have 1 plus cos x to the power of sine x over cos x to the power of sine x plus 1. And you see, this is the same as this, so that cancels away, and we just end up with cos x to the power of sine x. So this is our new integral. 2I equals x ln cos x to the power of sine x. Now, we can take that sine x out of the log using that log law. So you end up with x sine x times ln cos x. Here, we're going to use integration by parts. We say u equals x, du equals 1, dv equals sine x ln cos x, and v equals a bit of a jump, but cos x minus cos x ln cos x. And you can see this is done by doing a substitution, and then the usual way that you'd evaluate the integral of ln x. So, we want to evaluate x cos x minus x cos x ln cos x between 0 and pi over 2. And you can see that this is just going to be 0 at pi over 2 and at 0, so we don't have to worry about this. So now I just have this integral here, minus the integral of cos x minus cos x ln cos x. Now, we can integrate this one just fine, it's just, sine x. So we do that by like so, and we get minus 1. Now we're left with this integral, cos x ln cos x between 0 and pi over 2. Now, we're going to use integration by parts again. This time we're going to say u equals ln cos x, d equals minus sine x over cos x, dv equals cos x, v equals sine x. Now we have this evaluation here, sine x ln cos x between 0 and pi over 2. And this one we can't actually do immediately because at pi over 2, cos x is going to be 0, now we have ln 0. And that's just not something that we can deal with nicely. So we're just going to leave this as it is for now, and we're just going to evaluate the rest of this integral. So we have sine x times sine x over cos x. So sine squared x over cos x. And if we write sine squared x as 1 minus cos squared x, we can get sec x minus cos x. So evaluating this integral here, we end up with minus sine x from the minus cos x, and then sec x integrates to ln sec x plus tan x. So now we have, if we group this together with what we had before, we're going to evaluate this big thing here between 0 and pi over 2. Now, we can evaluate this at 0 just fine. I think it actually end up just becoming 0, right? So we have, sine x becomes 0, sine x becomes 0, and then we get ln 1, which is 0, yeah. So at 0, this is 0, so we just want to find the limit as this approaches pi over 2. And we already know that minus sine x is going to be minus 1. So really just have minus 2 plus the limit as x approaches pi over 2 of sine x ln cos x plus ln sec x plus tan x. Now, what we want to do is we want to combine this into one big logarithm. And we can't do that just yet because this one has a sine x in front of the log, but this one doesn't. So we can artificially make our own sine x in front of this by raising sec x plus tan x to the power of 1 over sine x, like so. So now that we can combine the logarithm, we have cos x times sec x plus tan x to the power of 1 over sine x. And as x approaches pi over 2, this sine x is going to be approaching 1. So we end up just getting cos x times sec x plus tan x, which is going to be 1 plus sine x. And as x is approaching pi over 2, sine x is going to approach 1. So we're just going to end up having minus 2 plus ln 2. And that's just going to be our answer right there. Question 3, we're going to integrate x arc cos x over 1 plus x squared between minus 1 and 1. Now, I'm going to tell you now, the solution that I'm about to show you is definitely not the easiest way. So I do encourage you guys to give this one a go. See if you can come up with something better, and maybe let me know in the comments. So, let's get started. We're going to start off by writing 1 over 1 plus x squared as a geometric series with a common ratio of minus x squared. So instead we end up having this integral of between minus 1 and 1, and then we write 1 plus x squared as minus x squared to the power of n, and we times it by the x from up here, and now we have arc cos x as before. We can bring the sum outside, and we can bring the minus 1 to the n from minus x squared to the n outside the integral, because that's not dependent on x. And now we just have the integral between minus 1 and 1, x to the 2n plus 1 times arc cos x. So here we can use integration by parts. We can say u equals arc cos x, du equals minus 1 over square root 1 minus x squared, dv equals x to the 2n plus 1, and v equals x to the 2n plus 2 over 2n plus 2. So now we just end up with this series here. We have sum from n equals 0 to infinity, minus 1 to the n, and then we want to evaluate arc cos x, x to the 2n plus 2 over 2n plus 2 between minus 1 and 1. which ends up being minus pi over 2n plus 1. We're going to add that to the integral of 1 over 2n plus 2, and then x to 2n plus 2 over square root 1 minus x squared, 2 minus 1 on 1. So here we're just going to focus on the rest of this integral here, x to 2n plus 2 over square root 1 minus x squared. And what we can do is we can write this as, instead of using 1 and minus 1 as the bounds, if we have 1 and 0 as the bounds and times it by 2, we can do this because this is an even function here that we're integrating. So double the integral between 0 and 1 is going to be the same as the integral between minus 1 and 1. And as well as that, we can also write this as x squared to the power of n plus 1. So now if we do a substitution for u equals x squared and du equals 2x dx, now we end up with the integral between 0 and 1 of u to the power of n plus a half times 1 minus u to the power of minus a half, which is actually the beta function of n plus 3 over 2 and a half. So if we write this in terms of gamma, we have gamma n plus 3 over 2 times gamma a half over gamma n plus 2, and we can say that the gamma of a half is just square root pi. So we have square root pi times gamma n plus 3 over 2 over gamma n plus 2. So all in all, we have this monstrous series here, sum from n equals 0 to infinity of minus 1 to the n over 2 lots of n plus 1 times minus pi plus square root pi gamma n plus 3 over 2 over gamma n plus 2. And we can reindex the sum by just, instead of from n equals 0, we start from n equals 1, and then we shift down all of the n's by 1. So now we, instead of having n plus 1, we have n. Instead of n plus 3 over 2, we have n plus a half. And instead of n plus 2, we have n plus 1. And we have the minus out front, so we can keep this as minus 1 to the n. And you can see that if we look at this minus 1 to the n times minus pi over 2n, this term is actually just minus pi over 2 times the natural log of 1 plus 1 from that power series. So we can just evaluate this term just like that. Now we're left with this nasty sum here. Sum from n equals 1 to infinity, minus 1 to the n, square root pi, gamma n plus a half over 2n gamma n plus 1. So to evaluate this, we can first use this identity here, gamma n plus a half equals 2n factorial times square root pi over 2 to the 2n times n factorial. And doing so by also using gamma n plus 1 equals n factorial, we end up having n factorial squared on the bottom, and our rest becomes minus 1 to the n times 2n factorial over 2 to the 2n as well. Now what we're going to do is we're going to write 1 over 2n as the integral between 0 and 1 of x to the 2n minus 1. We're going to write 2n factorial over n factorial squared as 2n choose n. And now we're going to write our sum like this. Now this is going to seem kind of crazy, but bear with me. So we have sum from n equals 1 to infinity of 2n choose n times minus 1 to the n over 2 to the 2n times the integral between 0 and 1 of x to the 2n minus 1. We're going to write this slightly differently, as if we take the integral to the very front and have this x to the minus 1 term, that's just 1 over x. And now we have our sum from n equals 1 to infinity of 2n choose n. And then we can group this minus 1 to the n and this 2 to the 2n as minus a quarter to the power of n, as well as this x squared to the power of n, to get minus x squared over 4 to the power of n inside the integral and the sum. And we can use this fact that 2n choose n times x to the n equals 1 over square root 1 minus 4x. And this is a result that you can get just from a binomial series, binary expansion. And this is true for the modulus of x being less than a quarter. Now we can see here that we're integrating between 0 and a quarter, 0 and 1, and we have minus x squared over 4. So this condition is going to be satisfied. So now we can write this here as this sum as just 1 over square root 1 plus x squared minus 1. And the reason why we have minus 1 is because this sum is from n equals 0 and this one is just from n equals 1, so we have to include that term back in as well. So bringing this all together, we have square root x squared plus 1 minus 1 over x times square root x squared plus 1. We can substitute u equals square root x squared plus 1. So du equals x over square root x squared plus 1. And we end up with the integral between 1 and root 2 of 1 over u plus 1, which is just going to be ln 1 plus u. And then we put in square root 2, we put in 1, and here we have it, pi ln 1 plus square root 2 over 2. So putting everything together, we have minus pi over 2 ln 2, plus pi ln 1 plus root 2 over 2. It gives us our answer as pi ln 1 plus root 2 minus 3 pi over 2 ln 2. So there you go. So question 4, this is probably going to be the easiest question that we're going to have to deal with. We have the integral between 0 and infinity times the sum of from n equals 1 to infinity of 1 over x squared plus n to the 4. So start off by just swapping the sum and the integrand. You can start off by swapping the sum and the integral. Yeah, the sum from n equals 1 to infinity times the integral between 0 and infinity of 1 over x squared plus n to the 4. We can just write this as arctan x over n squared with 1 over n squared out the front. We evaluate this, we just get pi over 2. And then we have the sum from n equals 1 to infinity of 1 over n squared, which is also pi squared over 6. So times it together, get pi cubed over 12. Not bad at all. The limit as n approaches infinity of the integral between 1 and n of 1 over square root n x floor square root x. So the first thing that we're going to do is we're going to do substitution for square root x. And the reason why I want to do this is because 1, we have the floor of square root x here, so doing a substitution will make that much nicer to deal with. And secondly, we already have a square root x on the denominator, and we can get rid of that if we do a substitution for it. So, say u equals square root x, get du equals 1 over 2 square root x dx. And now we have 2 over square root n, the integral between 1 and square root n, and 1 over square root floor of u. Now, we don't have any continuous parts of this integral anymore. There's no u's on its own hanging around anywhere. It's just floor u. So that means we can write this integral as a series plus some extra rectangular area. So the way we want to do this, we can split this into bounds between 1 and floor of square root n, and then whatever's left, which is floor of square root n and square root n. So this is going to be the series because now we've got integer bounds, and this is just going to be the leftover rectangle. So write this as a series from k equals 1 to floor of square root n minus 1, and now floor of x is just going to be k, because this is just that constant. And on the right integral over here, I've just replaced floor of x with the lower bound of the integral, floor of square root n. And now that this doesn't have any x component, this is just a constant, so we can integrate it nice and easily. And then we end up getting the fractional part of square root n with a square root floor square root n as this right integral over here. And now we're going to introduce the limit back in. So the limit as n approaches infinity of this thing over here. Now, what you might notice is that the fractional part of square root n is always going to be between 0 and 1. But the denominator, on the other hand, is the square root of the floor of square root n times by square root n. And this is just going to grow to infinity as n grows into infinity. So that means this is going to be 0. So now we just have the limit of this sum times 2 over square root n. Now if you look at the sum, that sum is going to be less than or equal to the integral, right? So 1 over square root k is going to be, the sum of 1 over square root k is less than or equal to the integral of 1 over square root x. So if we work out this integral right here, we get 2 lots of the square root floor square root n minus 1. And since there's a minus 1 here, we can say that this is less than or equal to 2 lots of n to the quarter. So if we times this by 2 over square root n, we now know that as n approaches infinity, 2 over square root n times the sum of 1 over square root k is going to be less than or equal to, as n approaches infinity, 4 lots of n to the minus a quarter. And as n approaches infinity, this is going to approach 0. So that means as n approaches infinity, this sum is going to have to be less than or equal to 0. But we know that our sum is going to be non-negative because we're only adding positive terms. So there's no way that our sum is going to be less than 0, but it clearly can't be more than 0. So that means the answer is 0. Alright, question 6. The integral between 0 and pi over 2 of 1 over 1 plus sine x squared times square root ln sec x plus tan x. So let's get started with a substitution for square root ln sec x plus tan x. So we take the derivative, we get sec x over 2u dx, and then we end up with 2 lots of the integral between 0 and infinity of 1 over sec x times 1 plus sine x squared, but du. And we can see that we've gotten rid of this nasty square root ln sec x plus tan x term right off the bat. So now we have 1 over sec x times 1 plus sine x squared as what we want to have in terms of u. Now, what we can do is we can write this as sec x over sec x plus tan x squared by multiplying top and bottom by sec squared. And we can say that 1 plus tan squared x equals sec squared x, and sec squared x minus tan squared x equals 1. So we can write this as sec x plus tan x times sec x minus tan x equals 1. And as such, we get sec x minus tan x equals 1 over sec x plus tan x. So now instead of sec x plus tan x squared, we can write this as sec x minus tan x squared. So yeah, we end up with sec x times sec x minus tan x squared. So now the goal is we want to write sec x and tan x as a function of square root ln sec x plus tan x to complete the substitution. Now, first thing that we can say is let's consider sec x plus tan x plus 1 over sec x plus tan x. We write this as 1 plus sin x over cos x plus cos x over 1 plus sin x. And then put this into one fraction. We have 1 plus 2 sin x plus sin squared x plus cos squared x over cos x 1 plus sin x. And then we can get 2 lots of 1 plus sin x on the top. And then that cancels with the denominator. So we just get 2 sec x as the result of sec x plus tan x plus 1 over sec x plus tan x, which is very handy. Now what if we do minus instead of plus? So sec x plus tan x minus 1 over sec x plus tan x. We do the same thing, we put it onto the same fraction, expand out the 1 plus sin x squared, and then we end up with 2 sin x times 1 plus sin x over cos x times 1 plus sin x, which we can take that away, and now we get 2 tan x. So we can write sec x and tan x as a function of square root ln sec x plus tan x, which is exactly what we need. So sec x equals a half, lots of e to the u squared plus e to the minus u squared, and tan x equals a half e to the u squared minus e to the minus u squared. So writing that all together to get the substitution done, we have 2 on the outside, and then the half from the sec x, and that ends up just cancelling. And then we have sec x plus tan x, but you can see that the e to the u squared terms are cancelling out, and then the e to the minus u squareds are adding together. So that half and that half add up to 1. So in total we end up with an integral between 0 and infinity of e to the u squared plus e to the minus u squared times e to the minus 2u squared. And we expand that bracket out, we have e to the minus u squared and e to the minus 3u squared. And this is just the Gaussian integral, so we can evaluate this. We have half square root pi and half square root pi over 3. And we end up with square root pi over 6 times 3 plus square root 3 as our answer. Next up, we've got question 7. We have the integral between 0 and infinity of 100 e to the x e to the minus x, and we take the floor of the result. Kind of interesting. So first, we can write this a little bit differently. We can write this as e to the x times e to the minus x over e to the x. And we can see that if we take a substitution for e to the minus x, we can get rid of the denominator. So we just end up with e to the x times e to the minus x can be written as 1 over e to the minus x to the power of e to the minus x. So we just get 1 over u to the u. So that's just integral now. 0 and 1, 1 over u to the u. So how are we going to do this? Well, we can write u to the u as x to the minus x, because the variable doesn't matter. We can write this as e to the power of ln of x to the minus x. Then we can take the minus x out the front of the log. So you have e to the minus x ln x. Now, we have the integral between 0 and 1 of e to the minus x ln x, and we can write the e to the minus x ln x as its power series. So we have the sum from k equals 0 to infinity of minus x ln x to the power of k over k factorial. Now what we can do is we can take out the minus 1 to the k over k factorial from here, and take it out of the integral entirely. So we just have the integral of x times ln x to the power of k. And this is actually an integral that I've done before on this channel. It's a special case of the x to the m ln x to the n integral. So we can use the same steps from before. Say u equals minus ln x, d equals minus 1 over x dx. And now we end up with e to the minus u to the power of k times minus u to the power of k times e to the minus u. And then we can take the minus 1 to the k from this term and multiply it by this one to get minus 1 to the 2k. And we end up with e to the minus u to the k plus 1 times u to the k. And this is very close to the gamma function. We just need to do a substitution. So v equals u to the k plus 1, dv equals k plus 1 du. And now we end up getting sum from k equals 0 to infinity, 1 over k factorial times 1 over k plus 1 to the k plus 1 times the integral between 0 and infinity of e to the minus v, v to the k. And this here is just the this is just k factorial. So now with this lovely sum here, sum from k equals 0 to infinity of 1 over k plus 1 to the k plus 1, which is the sum from k equals 1 to infinity of 1 over k to the k. Now, how are we going to do this? Good thing is we don't have to do this, because we were asked to times this by 100 and then take the floor of the result, right? So really we just have to approximate it to 2 decimal places, and we've got our answer. So it's pretty clear that after a while this series is going to end up being too small to even contribute to 2 decimal places. So we could just take the first like bunch of terms and then just add them together. So yeah, we end up with 1.29 as our answer, times it by 100, 129. And there you go. Question 8, the integral between 0 and infinity of ln squared x times 1 plus x squared over 1 plus x to the 4. Let's have a look. We're going to start by splitting this integral up by the numerator. So we have ln squared over 1 plus x to the 4, and then x squared, ln squared 1 plus x to the 4. Now, if you just look at this first integral here, and do the substitution u equals 1 over x, what we're going to get? Well, our bounds are going to stay the same, because they're going to flip once from the substitution, and then we can use the minus sign to flip them back to normal. And now we have ln squared times x squared over 1 plus x to, ln squared over x squared times 1 plus 1 over x to the 4. And then if you times the bottom by x squared, we just get x squared ln squared over 1 plus x to the 4. So this integral is the same as this first integral here, which is this one. So really we just have 2 lots of this first integral that we want to work out. So I equals 2 lots of the integral between 0 and infinity ln squared x over 1 plus x to the 4. Now, if we do a substitution for x to the 4, watch what's going to happen, okay? Watch what's going to happen. We have 2 lots of the integral between 0 and infinity times a quarter ln t squared over 1 plus t, and then times it by the result from substitution, a quarter times t to the minus 3 quarters. So all in all we get 1 over 32 times the integral between 0 and infinity of t to the minus 3 quarters times ln squared t over 1 plus t. Now, let's consider this parameterization right here. F of alpha equals the integral between 0 and infinity t to the alpha minus 1 over 1 plus t. We take the derivative of it once, we end up with ln t, right? So we take the derivative of it again with respect to alpha, we get ln squared t. And this is exactly what we want. This happens to be our integral. If we take a 1 over 32 in front of it and plug in a quarter into alpha, this is what we have. And this integral here is actually f of alpha. This is actually just the beta function as well. So f of alpha equals beta alpha 1 minus alpha, which is gamma alpha times gamma 1 minus alpha over gamma 1. And gamma 1 is just 1, and then we can use the Euler reflection identity for the numerator to say this is pi cosec pi alpha. And we just take the derivative of it with respect to alpha twice. So do it once, we get minus pi squared cosec pi alpha cot pi alpha. Do it again, get pi cubed cosec squared pi alpha times cosec pi alpha plus cot pi alpha. And we plug in a quarter, we get 2 pi cubed times square root 2 over 1. We get 2 pi cubed times square root 2 plus 1. And then we divide that by 32. And we get our answer as pi cubed times square root 2 plus 1 over 16. And the last integral that we're going to do is going to be the integral between 0 and e of ln x times r sine x. So first we're going to do integration by parts. We're going to say u equals r sine x. So du equals 1 over square root 1 plus x squared. Say dv equals ln x. So v equals x times ln x minus 1. So this is what we're working with now. We want to evaluate r sine x times ln x minus 1 between 0 and e. And this actually ends up becoming 0, because when you put in e, ln x minus 1 is 0. If you put in 0, x is 0. So this just goes to 0. So I just have this integral here that we want to worry about, minus the integral between 0 and e of x times ln x minus 1 over square root 1 plus x squared. And you can see that if you were to make a substitution for square root 1 plus x squared, not only does that get rid of the denominator, it also gets rid of the x that's on the top. You say u equals square root 1 plus x squared, du equals x over square root 1 plus x squared times dx. So now we have the integral between 1 and square root 1 plus e squared times a half ln u squared minus 1 minus 1. And we can evaluate minus 1 just fine. So we get square root 1 plus e squared minus 1. And now we have minus a half times the integral between 1 and square root 1 plus e squared. And we can split up ln u squared minus 1 into ln u plus 1 plus ln u minus 1, like so. And we just evaluate those as follows. So just by doing a substitution for, u plus 1 and u minus 1, we end up getting these. And we just evaluate them like so. Now this is kind of a long process, as you can see. It's a bit of expanding out. But yeah, we do get some simplifications, like inside of this natural log here. The square root 1 plus e squared times ln, and then the square root 1 plus e squared, and the 1 and the minus 1, and the square root 1 minus e squared, 1 plus e squared, sorry. They all go away, and we just have ln e squared, which is just 2 ln e, which is just 2. So you have 2 square root 1 plus e squared minus 2 square root 1 plus e squared, and those both go away. So you just end up getting this value here, this ln square root 1 plus e squared plus 1 over square root 1 plus e squared minus 1, which is just two lots of arccoth square root 1 plus e squared. So simplifying all together, we have square root 1 plus e squared minus 2 plus ln 2 minus arccoth square root 1 plus e squared. And there you go.